So now we're going to look at exercise hello triangle indexed, which is 2.2. And if we run it, it's actually not rendering a triangle. Well, it's rendering two triangles that form a rectangle. And while we could render two triangles just like we rendered a single triangle before, this time instead of calling GL draw arrays, we're calling GL draw elements. And what draw elements does differently is that yes, it expects a VAO, which we have set up. It expects a shader program, but it also expects a buffer of indices. The indices are indexes into the vertex data such that we construct our primitive, in this case a triangle, by specifying three indices. So if we look up at our vertices array, we're going to end up forming two triangles, yet we're only specifying 4 vertices. And then in our buffer of indices, we're going to have first a triangle made up of index 0, 1, and 3, meaning this vertex, and then the one at index 3. And then the second triangle is formed from 1, 2, and 3, so it's formed from these 3 vertices. Without these indices, if instead we were using GL draw arrays, then here we would have to have 6 vertices, 3 for the first triangle, 3 for the second, and that would mean that the vertices at indexes 1 and 3, they'd have to be repeated in the vertex data. That may not seem so bad with a small set of vertices, but if you imagine for a much larger model, you're going to typically have many, many more shared vertices that are going to have to be stored redundantly. And also the problem is that, as we'll see later, our vertices are going to be accompanied by attribute data. So each vertex might end up being something significantly more than just 3 floats. It might end up being 12 floats or beyond. So it's an even greater savings then if we don't have to store redundant vertices. So now, as I said, everything in this example is exactly the same, except now we're going to have something you might call an element buffer object, which will have the indices data, and this has to be set up before we call GL draw elements. So here, when we create our VBO and our VAO, nothing is changing there, except now we also have another buffer for EBO. We're binding the VAO just like before, setting up the VBO just like we did before, same attrib pointer setup. That's not changed at all. But now for EBO, we're going to call GL bind buffer, this time specifying type element array buffer, not regular array buffer, as we do for our VBOs. And having bound this buffer, we then want to put the indices data into it, just like we do with buffer data here for the vertices, except again here you're specifying element array buffer, not a regular array buffer. And so now the EBO is actually ready to go. We don't associate it with a VAO the way we do with the VBO. VAOs do not make reference to these element buffer objects. Instead, it's simply the case that when we call GL draw elements, whatever is currently buffer bound with GL element array buffer, that is understood by draw elements to be where the indices are specified. In fact, if we don't have EBO bound at this point, if there is no currently bound element array buffer, then this call would crash. Note that we're specifying, of course, the type of the primitives. This is the number of vertex indices that are going to be read. This is the type of the indices, not the type of the vertices themselves, the type of the indices. They're unsigned ints. And the 0 here is an offset, so you can have it read from some index other than the first index. So that's all that's different here, except one last thing. We created the EBO, so we should also delete it like any other buffer when we're done. So we call delete buffers down here with EBO. So now let's look at exercise 3.1, shaders uniform. And here it's rendering a triangle, but if we wait a moment, you'll see that it's actually changing its color, pulsing slowly over time. The first thing that's different here is in our fragment shader, we now have this variable of type vec4 called ourColor, and as it says, it's a uniform variable. Uniforms are variables in our shader program that are global throughout the program, and in fact are not allowed to change in the running of the program. And before we run the program, before we call draw arrays or draw elements, we have to set up the values for the uniforms first. They're basically inputs from outside the shader program. And be clear, when we say they're unchanging during the run of the program, that's the shader program, which runs once each frame. So frame to frame, in this example, we're changing what the ourColor value is. And as you can see in the code, it's simply taking whatever the ourColor is from the uniform and setting that to be the frag color. looking down at the loop, we've actually in this case gone back to draw arrays. We're not using draw elements and we're not using indexes anymore. We could, but there's no reason to do so, so we're just going back to the more straightforward method in this case. But before the draw call, we're calling GL uniform 4f. 4f here means a vector of 4 floats. Because OpenGL is codified for C and C doesn't have function overloading, it's the case that in OpenGL you have a number of functions where there are many variants for different kinds of input. So this is the version of GL uniform that takes in a vector of 4 floats, which are these 4 float values here. And when you call GL uniform, the shader program whose uniform we are setting has to be the currently enabled program. So we have GL use program up here for our shader program. But the call also has to specify which uniform variable we're setting the value for, because there could be many. So that's why here you're specifying vertex color location, which is just an int value that has been defined up here by call to get uniform location, pass in the shader program, and the name of the uniform variable, which in this case is our color. And be clear that uniform location actually is not changing frame to frame, so this could just be done outside the loop. So that's how we set up a uniform value. And in this specific case, the uniform is being used as a color value where the red is 0, the blue is 0, the alpha is 1, and the green value is going to vary frame to frame based on the current time, which we're getting from GLFW, and then using a sine function to have it vary in a pulsing gradual transition way. Sine, of course, always returns something in the range of -1 to +1, and so frame to frame, the green value is pulsing up and down from black to a certain green shade in a smooth curve. Now I did say that uniforms are not meant to be mutated in the course of the shader program, so let's actually see what happens if we do try and mutate the uniform here. I'm going to modify our color, just set it to this white value, save. I'm going to come over here and build the project, run the program. And well, it didn't crash the program, but you can see in the console we have some errors now. There's first a compilation failure, and then of course, because it failed to compile it, we also can't link. And it's telling us that there's an assignment to uniform our color. And you're just not allowed to assign to uniform, so that's why that's invalid. So the compiler caught the error. Now let's look at example 3.2, shaders interpolation. I'll run it. And you can see we get a pretty rainbow triangle. So what's going on here? Well, firstly looking at the shaders, whereas before we just had the one input to our vertex shader, now we have a second input. Notice it says location 1. This is going to be a color value, as the name indicates, also a vec3. Also now, in addition to assigning to GL position, which is just an automatic variable that is created implicitly, we don't have to create it ourselves, it's always there. We're now creating another output variable called our color vec3, which is going to be passed down the pipeline. So if we had geometry and tessellation shaders, we could get this value there, but we don't have such shaders. We do, though, of course, have our fragment shader, and so our fragment shader needs to accept as input now our color. And I believe the fact that the name and type matches is significant. I'd have to test this and look at the docs. I can't see any reason why you'd make them not match. It otherwise, I think, might have to do with the ordering. So if we had multiple output variables, multiple input variables, they may just match up in order. I think it might work that way instead, actually. I'd have to check. Anyway, as we have it configured here, it works. Output of our color is going to be accepted as input here. And now in the fragment shader, when we set frag color, we're setting it to the our color input. But understand in the output shader, for each vertex, we're spitting out a different color. And for a triangle, then the question is, well, what does the fragment receive? For a pixel within a triangle, which of those colors do we get? Well, what we get is the interpolation thereof, the perspective correct interpolation, as we discussed in earlier videos. In the whole rasterization process, the hardware is figuring out how to interpolate these values in a perspective correct way. And that's what we get here as input to our fragment shader. So aside from the shaders being different, what's different in our rendering loop? Well, the rendering loop is nothing new here. It's just like our actually earliest example. We're just rendering the triangle as currently configured by the VAO. No indices this time again, we're just using draw arrays. So nothing new here, but if we go look at our vertices array, now it contains not just positions, but colors. And notice the layout where it's for each vertex, it's first the position, the 3 floats, followed by 3 RGB floats for the color. And whereas before we just had one vertex attrib pointer call specifying where the vertices are and how they're laid out in the array, now we're going to have a second vertex attrib call. Notice it says index 1 specifying how the colors are laid out. And this top call actually also changes because where it was here 3 times size of float for the stride because the positions were just spaced 3 floats apart. Now they're 6 floats apart. It's from here to the next one, right? Well, same thing for the color attributes. They are spaced 6 floats apart. Here to here is 6 floats. But we also need to specify an offset that starts here because this is where our first color is, of course. So that's why this is a void pointer of 3 times size of float, not 0. And do not forget to call enable vertex attrib array, otherwise it would not go into effect. So having set up both the indexes of VAO, index 0 and index 1 for the vertex data itself, and then the attribute of the color, when the shader gets called, it's going to receive 2 inputs. One at location 0, as in index 0 of the VAO, and the other at location 1, index 1 of the VAO, which is our colors. So again, understand the relationship between the VAO and the VBO or VBOs is that the VAO is a structure of, I believe on most OpenGL implementations, the max is capped at 16. I believe that's usually the case. So you can have up to 16 indexes for your VAO, potentially pointing to different VBOs, but in this case it's just 1. And for each index in the VAO, it also has information about how the data is laid out within the buffer. That's why when we come down to the draw call, we don't need to have the vertex buffer object bound, we just need the vertex array object bound because it internally has references to any relevant VBOs. And I believe actually in the prior video I may have said it was safe to delete the VBO before this call. Well, I think we got away with it in that prior example because there aren't any subsequent allocations on the GPU side that might potentially overwrite the memory that VBO was occupying. But in a larger program, it might be the case that if you delete the buffer, I believe just like when you might manually free memory on the CPU side, the danger is that that chunk of memory might subsequently get overwritten by later allocations. So while the data of this VBO is in use, even though we don't need to have the VBO bound, I believe it's the case that it's not safe to delete it. So we should only delete the VBO here when we clean up. So let's run the program again and see this top vertex. This was set to the color of RGB 001 as in full blue. This here was 010 as in full green. This was 100 as in full red. And then for the fragments in between, for the pixels in between, it's interpolating between those color values. That's why it smoothly transitions and you get the full colors of the rainbow all in this one triangle. So now we're going to look at texturing with example 4.1. Let me run that here and you can see it's demonstrating how to paint a texture onto our 2 triangles. And to bring in texturing, we're going to need to be able to load images from files, in this case from a JPEG. And so for that purpose, we're adding a new dependency, s2b_image. Now we also have these other 2 includes, filesystem.h and shader_s.h. These provide abstractions for working with the file system for loading files and for encapsulating a shader as a class. I'm not going to cover that. It's not anything specific to OpenGL. It just abstracts around it in a little bit more convenient way. And so now when we load a shader and set it up for use, it's done with this constructor call where you pass in the file path to the vertex shader and then the file path to the fragment shader, and now those are stored in separate files. Before we were just writing them inline as strings, but as your code gets larger, of course, it's better to split them into separate files. It's also advantageous this way because if we want to change our shader code without changing of our C++ code, now we don't have to recompile. If I come over here and make a change to my shader code, I just run the executable, and because the shaders are loaded and compiled at runtime, then I don't have to rebuild the executable to change my shader code. So with this exercise, we've cleaned up the boilerplate a little bit. Otherwise, what's new here is now we're working with a texture. And so now in our fragment shader, rather than just taking a solid color and assigning it to every pixel of our polygons, we're going to read a color value from a texture. And two-dimensional textures in GLSL are represented with a type called sampler2D. That's going to be passed into the shader as a uniform, which we're going to have to set up in the C++ side, of course. But once we have our sampler, we can sample from it, we can read values from it with the texture function, specify which sampler, and then the coordinate, which here is an input variable that is going to be passed from the vertex shader, a vec2 for a u and a v value for texture coordinates. And note that this other input variable, our color, is being ignored in the shader. We could just get rid of it. It's a hangover from a previous exercise, and I think it comes into play in a later exercise, so that's why it's here. But we don't really need it, of course. As for the vertex shader, it's getting 3 inputs. Now a third attribute for the UV coordinates of the vertices. So atex coord here is for this vertex, what is the associated UV attribute? And we're creating 2 outputs that get passed as input to the vertex shader. We set GL position as normal. We're setting our color again like we did before. And we're setting the output variable text coord. I don't know why he's reconstructing a new vec2 value out of the x and y of atex coord, because it of course already is a vec2, so we should just be able to write this for the same result. Not sure why it was written that way. This way of course will work. So that's what's going on in our shaders. And now what we need to know is how do we set up, on the C++ side, how do we set up this third input? Looking back at the C++ side, you see we have the indices for the 2 triangles because we're going to be using draw elements to draw this time. We could of course just use draw arrays and not use indices, but then we'd have to duplicate some of these vertices within the vertices array, and it's just a little clearer if we don't have to do that. So now we're adding, in addition to the 3 position floats and the 3 color floats, we now for every vertex also have 2 texture floats, the U and the V. So the top right gets 1, 1, the top right of our texture, the bottom right gets 1, 0, the bottom right of the texture. The bottom left of our rectangle is mapped to the bottom left of the texture, 0, 0, and the top left of our rectangle is mapped to the top left of our texture. So for these texture coords, we need to set up the third attribute with GL vertex attrib pointer index 2, an attribute that will have a count of 2 values, because it's just 2 floats, not 3 this time. They're still floats, still don't want to normalize any fixed point values. And the stride between vertices now is 8 times the size of a float because each vertex has 8 values. Notice we have to update that for all the attributes. And the offset to the third attribute is 6 floats in. It's the 6th float within the vertex. So that's our vertex attrib pointer call. Don't forget to enable the vertex attrib array with index 2. This should be a familiar thing by now. We're now just setting up a third attribute as input for the vertex shader, here coming in as a text coord. But what about the texture? First thing we need to do is create a texture. So we do so with glgen textures, much like we have done with other kinds of objects. We then bind the texture so that certain calls that follow, like this one here, text parameter I, it's going to apply to this texture which is currently bound. And with these calls to text parameter I, the I standing for integer, to distinguish from calls where floats are accepted for parameter values, we're configuring certain parameters of the texture, including the GL texture wrap S value, the GL texture wrap T value, texture min filter, texture mag filter. These are the most essential parameters. What the texture wrap parameters determine is what happens when you try and sample from a value that's out of the range of 0 to 1. Well, here for the S and T dimensions, which correspond to U and V. In different contexts, we say UV for texture coordinates. In other contexts, we say S and T, but they mean basically the same thing. Anyway, we're setting the wrapping policy for both dimensions to be repeat, such that, say, the U coordinate 1.1 would be interpreted as 0.1. 2.1 would also be 0.1. 3.1 would also be 0.1. So with repeat, we're effectively ignoring everything but the fractional component of the value. And this gives the effect of the texture wrapping. And we can see what effect this would have if I were to change these values here. I'll change them to 2. Save, come over here and build the project. Run the program. And now you can see the texture is repeating 4 times. What was just this lower left quadrant stretched over the whole rectangle. Now it's that same thing repeated 4 times because of our wrapping policy of repeat. There are several other options to repeat. I'm not going to go over them here, so you can look those up. but that's what's going on with the wrapping parameters. As for texture min filter and mag filter, min as in minification, mag as in magnification. Min and mag have to do with bitmap levels, which I discussed in a prior video. And linear here refers to bilinear filtering, which is again something I've explained in a prior video. This effectively is determining what happens when our UV chord does not correspond to the precise center of a texel, to an individual color value in the texture. And with bilinear filtering, then the color you get is not a precise match for just that pixel. It's a weighted average of that pixel and its immediate neighbors. Again, this is something I explained in a prior video, and there are many sources that explain the concept, so I'm not going to delve into these details here. Having set the texture parameters, we need to load the actual data into the texture, and so that's going to require reading the JPEG file into an array of bytes, and so that's what this STBI load function is doing. And for this call, it's going to set an int width and an int height, and also the number of channels, though we're not actually going to use this in this case because we know what the number of channels in this image happens to be. It's 3, it's RGB. Upon success, data here will be non-null, otherwise we're going to come down here and print out an error message. But assuming we've successfully read the image, then we're going to call textImage2D. The 0 here specifies the bitmap level we are defining the texture for. Again, bitmaps are a concept I talked about in a prior video. I'm not really going to go into it here. This RGB parameter is saying that the internal format, what we're storing on the GPU side, is going to be in the format of RG and B, red, green, and blue. Then we have the width, the height, and the 0 here is the width of the border for the image. I'm not sure why you would give your textures borders, but that is an option. The second RGB is specifying the format of the data we're reading from data, and unsigned byte specifies the format of each value. In this case, they're unsigned bytes. So with the texture data loaded into our texture object, we call generate bitmap to generate different levels of bitmaps. And I'm pretty sure this step is not required, but you do generally get better results. You get better texturing. Anyway, now we have a texture object ready to use. Last thing, we should deallocate the data that was allocated by STBI. This is no longer needed for our texture object because the data has been copied into the texture object. Lastly, within our rendering loop, nothing here is new. Just make sure that the texture is bound before we draw. Note here this method call on the shader object, on the class encapsulating the shader. The call to use here just sets the program as active by calling GLUseProgram. And very last thing here actually is, well, having now created a texture object, like everything else properly, we should clean it up before we exit. So we should delete the texture. Let's look at the next example, 4.2, textures combined. And now what's happening is that we've loaded 2 textures, and for each pixel we're producing a combination thereof. We're blending between colors of 2 textures for each point on our rectangle. Our vertex shader is unchanged from the prior example, but now the texture shader, we have 2 uniforms, 2 textures, texture 1 and texture 2, and we're going to use the mix function to get an interpolation between these 2 texture samples. And we're doing so with the value 0.2, meaning that the second one contributes 20% and the first one contributes 80%. And that is how we get the frag color. So now that we're creating 2 textures, we need 2 texture handles, texture 1 and texture 2. And we do the whole process we saw before to create texture 1 with container.jpg. And we just do the exact same thing for texture 2 with awesomeface.png. In this case though, notice that it's RGBA, there's an alpha channel, both in the data we're reading from and the texture we're writing to. We want to actually store that alpha channel, because if we look at this ping, you'll note that there are some actually transparent pixels. Not the whites of the eyes, but everything around the circle is transparent. Now, aside from creating a second texture, the other thing we have to do differently now is we actually have to set the uniforms. Strangely, in the previous example, we created a uniform variable and created that texture, but we didn't explicitly set the sampler2D uniform value to that texture. Because what happened there is we only had one texture, so implicitly in the shader, it couldn't have been anything else. Here though we have 2 textures, so we have to set up the uniforms explicitly. And so this call to ourshader.use, that calls GLUseProgram for our shader to make it active so we can set up its uniforms. And here for uniform variable called texture1, we're setting its value to 0. And here this is doing the same thing for texture2 with the value 1, but here it's using a convenience method of our shader class to do so. So now this means in our fragment shader, texture1 will have the value 0, texture2 will have the value 1. So sampler2D, it really is actually just an integer value, but it's an integer value representing one of the texture mapping units. And so when we call texture and specify value 0, it's saying we want to read from the texture mapping unit 0. Now, before we draw, we have to make sure that texture mapping unit 0 is set to our first texture and texture mapping unit 1 is set to our second texture. So that's what these lines do. We're saying make texture mapping unit 0 the active texture and bind texture 1, make texture unit 1 the active texture mapping unit, and then bind our texture 2 handle. If you're wondering, well, what is the maximum number of textures I can use in any one shader? Well, that depends on your hardware and driver, but I believe the minimum required by the OpenGL standard is 16.